Hello everyone, welcome back. Today we are tackling a classic and fundamental Leetcode problem, maximum depth of binary tree, problem number 104. It's marked as easy, but it's a fantastic way to understand the fundamentals of tree traversal. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given the root of a binary tree and we should return its maximum depth. The depth of a binary tree is the number of nodes along the longest path from the root node down to the farthest leaf node. For example, in this tree, one of the path goes from root node 3 to leaf node 9 and the length of this path is 2. Another path goes from root node to leaf node 15 via node 20 with length as 3. And the final path goes from root node 3 to 20 to leaf node 7. And this path also has length 3. And when we compare these three paths, the longest one is of length 3. So the longest depth of the tree will also be 3. Alright, let's talk about how to solve this. We can approach this problem in a few ways, including an iterative depth first search, aka DFS, and a breadth first search, aka BFS, but we'll start with the most intuitive one, which is recursive DFS. Our main goal is to find the maximum depth of the tree that starts at the root node 3. And let's think about this from the perspective of node 3. How much does this node contribute to the maximum depth? Well, since it's a valid node, it contributes 1 to the maximum depth. And also it's a root node. So any path starting from it to the leaf node must include it. So it will always contribute 1 to the total length. And this is true for any valid node in the tree, that it adds 1 to the depth of any path that passes through it. So given that the rest of the depth must come from the longest path in its subtrees, which are the left subtree and the right subtree. And now suppose the left subtree contributed the depth of 1 and the right subtree contributed the maximum depth of 2. Then which depth should we choose? The answer is the maximum one because we want to calculate the maximum depth of the tree. So this gives us the recurrence relation as 1 plus maximum of depths of its left and right children respectively. So our problem boils down to finding the maximum depth of the subtrees starting at node 9 and node 20. First, let's find the depth of the subtree at node 9. And since node 9 is a valid node, it contributes 1 to its maximum depth. And then we need to add the maximum of the depth of its children. So we go to its left child to get its contribution, but it is null. And since the depth is the count of nodes, a non-existing node contributes 0. So this brings us to the base case, that is, when the node is null, we return 0. Then we try the right child, which is also null, so it also contributes 0. Therefore, the total depth of the subtree rooted at 9 is 1 plus maximum of 0, 0, which is simply 1. And now we are done with the left subtree, which contributes a maximum depth of 1 to node 3. So the maximum depth of node 3 will be equal to 1 plus maximum of the depth we got from the left subtree, that is 1, and the right subtree, which we have to calculate. So now we go to node 20 and it has two children, 15 and 7. And just like node 9, the depth of node 15 and 7 will also be 1 each. So the depth of the right subtree with 20 as a root node will be 1, which we get from node 20 itself, plus maximum of the depth of its children, which is equal to 1 plus maximum of 1, 1 equal to 2. So this contributes 2 to the parent node. Hence we calculate the final answer as 1 plus maximum of 1, 2, which is equal to 3. So the maximum depth of this tree is equal to 3 itself. Now the time complexity of this approach is O of n, where n is total number of nodes in the tree Because to be sure that we have found the longest path, our algorithm must visit every single node in the tree exactly once. And the space complexity will be O of h, where h is the height of the tree. And this is because the memory is used by the recursion call stack, which is proportional to the height of the tree. And for the balanced tree, the height of the tree is roughly log of n, which is memory efficient. But in the worst case, tree may become completely unbalanced, where every node has a left or right child, making it look like a linked list. In this scenario, height is equal to number of nodes, making the space complexity O of n. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on the left and Python on right. First, let's handle the base case. If the root node is null, we have reached the end of a branch, so we simply return 0. But if the node is not null, then we make two recursive calls, one to find the max depth of the left subtree and another for the right subtree. And then the maximum depth of the current node is equal to 1 plus maximum of the depths returned by the left and right calls, which we return as the answer. Now let's see how we can solve this problem using iterative DFS. This approach is very useful to avoid recursion, which can sometimes lead to a stack overflow error if the tree is extremely deep. The core idea is to simulate recursive DFS using our own stack in a process that is very similar to pre-order traversal, where we process the root node first and then its children. This makes sense because in the recursive solution, we first dealt with the current node by adding 1 to its depth and then we handled its children. And that parent first logic is the core of the pre-order traversal that we will be mirroring here. A key difference from a simple recursive traversal is that we must manually keep track of the depth of each node. In the recursive version, the call stack handled this for us implicitly, but here we have to track it ourselves. That's why we will be storing the pairs of node and depth on our stack. As we are running pre-order traversal, first node we will push on stack will be node 3 along with its depth, which is 1 if we go from top to bottom. Let's also initialize our answer max depth initially equal to 0. Now we will loop through this stack until the stack isn't empty and we haven't processed all the nodes in the tree. So we pop out the top element, which is node 3 with depth equal to 1, and this is the maximum depth we have seen so far. So we update the maximum depth to 1 and we add its children back to the stack, which are 9 and 20. Typically, in a pre-order traversal, we process the left child first and right child later. And since stack is the last in first out, aka LIFO data structure, we will push right child onto the stack first and left child later. So we will push its right child, that is node 20, with the depth equal to depth of its parent plus 1. Depth of its parent was 1. So this gives node 20's depth as 1 plus 1 equal to 2. Similarly, we will push node 9 with depth 2 as well. And again, since the stack is not empty, we pop out node 9 as it is at the top of the stack and update the maximum depth to 2. And since node 9 has no children, we don't push anything new and continue to the next iteration where we pop out element 20 with a depth equal to 2. So maximum depth says 2 only. And then we push its children onto the stack, which are 7 and 15 with depth 3. And again, we pop out the top element, which is 15 with depth 3. So we update the maximum depth to 3. And since 15 doesn't have any children, we won't push anything. And in the next iteration, pop out element 7 with depth equal to 3. And the maximum depth is already 3. So there will be no change. And now the stack is empty. So our loop terminates with maximum depth equal to 3. Now, just like the recursive version, the time complexity of this approach is O of n because we still have to push and pop every node onto our stack exactly once, and the space complexity will be O of h, where h is the height of the tree. Since the maximum number of items we store in our explicit stack at any time is equal to the height of the tree, This is also same as the recursive version. But here we are using memory from the heap for our stack, not the function call stack. Now let's break down the iterative DFS code. First, as always, we handle the edge case, which is if the root is null, then the depth should be 0. Next, we set up our stack to store a node and its depth together. In Java, here we are using two separate stacks, one for the nodes and another for their corresponding depths. Another way can be that we can use a single stack that holds a custom pair object. I have included that code in a link in the description below if you'd like to see that pattern. In Python, we can use a single stack holding node and depth tuple, and once we have initialized the stack, we push the root node and its starting depth of 1. We'll also set our answer maximum depth initially equal to 0. Now we will run the while loop as long as stack is not empty. And first thing we do is we pop out the current node and its depth from their respective stacks and compare this depth with the max depth and update it if we have found a new deeper path. And then if this popped node has children, we push them onto the stacks with the depth incremented by 1, as now we have gone one level deeper. We add the right child first and then the left child to ensure we explore the left path first. And once the stacks are empty, that means we have visited all the nodes in the tree and the loop terminates. And now we can return the final max depth as our answer. And finally, let's cover the breadth first search or BFS approach. It's another iterative solution that also avoids recursion. The core intuition here is that the maximum depth of a tree is simply the number of levels in it. Since BFS naturally explores a tree one level at a time, we can count how many levels we pass through to find our answer. And typically in a BFS, we use a queue, which is a first in first out data structure. The first thing we check is if the root is null. If it is, then the depth is 0. Otherwise, we create a queue and add the root node 3 to it and initialize our level or depth to 0. Similar to iterative DFS approach, we will start a loop which continues as long as queue is not empty. And inside this loop, we are going to process one entire level at a time. So first we get the size of the queue, which is here equal to 1, which tells us number of nodes we must dequeue to completely remove that level. So we dequeue only one node here, which is node 3, and add its children that are 9 and 20 to the queue, and we increase our depth to 1 because now we have processed one level, and we start the next iteration, and the queue size is now 2. So we have to remove 2 nodes from it. So we dequeue nodes 9 and 20, and node 9 doesn't have any children, so we don't enqueue anything, but node 20 has 2 children which are 15 and 7, which we enqueue into the queue. And now since we have processed this level, the depth of the tree is now 2, and we start the next iteration and the queue size is again 2. So we dequeue 2 elements from it which are 15 and 7, and since they are leaf nodes, we don't enqueue anything back. And since we have processed this level, now the depth of the tree is 3. And now since the queue is empty, our iteration stops. And finally, the depth of this tree will be 3, which we will return as the answer. Now the time complexity of this approach is again O of n. Since we enqueue and dequeue each node only once, and the space complexity will be O of w, where w is the maximum width of the tree, because the queue will hold at most all the nodes at the widest level of the tree. For example, here we had the maximum width of 2, so the queue was holding 2 elements at a time. In the worst case, for a complete binary tree, the last level can have up to n by 2 nodes, making the space complexity O of n. For this solution, we'll use a queue to process the tree level by level. After handling the null root case, we'll initialize the queue with a root node, and let's also initialize the depth counter to 0. Now we run the while loop, which runs as long as the queue has nodes to process. And inside it, first thing we do is get the level size, which is number of nodes at the current level. And then we run an inner for loop which runs exactly level size times, where we dequeue a node and enqueue its left and right children if they exist. And once the inner loop is done, we know that we have finished an entire level. So we increment the depth counter, and after the main loop finishes, the depth variable will hold the total number of levels, which is our answer. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.